hơn để có thể có cái ứng dụng rất là sâu rộng trong khoa học kỹ thuật trong đời sống. Thế thì chúng ta tiếp xúc với chương 1, và tôi nhắc lại là chương 1 thì muốn hiểu được thì chúng ta trả lời được 2 câu hỏi quan trọng thôi, đó là tại sao các cái nguyên tử nó lại có thể đứng lại với nhau để hình thành tinh thể. Và chúng ta đã chứng minh rằng là có rất nhiều cái loại liên kết, đúng không? Và cho dù liên kết nào thì chúng ta thấy rằng là chúng ta đã chứng minh được bằng cơ học cổ điển cũng như là cơ học lượng tử rằng là khi các nguyên tử đứng lại với nhau thì năng lượng bị giảm xuống. Để nguyên tắc cực trị, cực tiểu năng lượng là được thể hiện ở trong cái việc mà các cái nguyên tử khi tham gia liên kết. Và để chứng minh điều đó chúng ta cũng đi lại giới thiệu, dù là học rồi nhưng mà đã giới thiệu cách rất là hệ thống, từ việc hiểu nguyên tử thế nào và sau đó thì các nguyên tử khi tham gia liên kết thì để chúng ta giải quyết cái bài toán ra làm sao. Thế thì như vậy chúng ta đã trả lời xong câu hỏi số 1, nghĩa là các cái loại lực liên kết để hình thành của các nguyên tử để hình thành tinh thể. Và câu hỏi thứ 2 rất là quan trọng, là thế thì các cái nguyên tử nó sắp xếp thế nào? Cái định nghĩa ban đầu về việc mà các cái nguyên tử sắp xếp trật tự tuần hoàn ấy, thì cái từ nó chung trật tự tuần hoàn là thế nào? Nó có giới hạn không? Nó vô hạn hay cứ kiểu trật tự tuần hoàn nào được chấp nhận không? Thế thì sau cái định nghĩa như vậy thì chúng ta phải tìm hiểu có rõ. Và rõ ràng là để hiểu được cái tính trật tự tuần hoàn thì chúng ta phải hiểu về các cái dạng hình học, đúng không? Không gian 3 chiều, có thể là 1, 2, 3, nhưng mà chúng ta phải hiểu về cấu trúc hay là dạng hình học của cái tinh thể, và chúng ta phải tìm hiểu xem là thế nó sắp xếp như thế nào. Thế để trả lời câu hỏi đó thì cái phần 2 chúng ta đang đi tìm hiểu, đúng không? Thế chúng ta hiểu đến đâu rồi? Thế nên với cái mục câu trả lời câu số 2 ấy, thì cách tiếp cận thế nào? Thế thì cái cách tiếp cận quan trọng nhất ở đây ấy, thì muốn giới thiệu với các bạn là người ta đã hiểu về cấu trúc tinh thể vật rắn ở thế kỷ trước rồi. Ở thế kỷ trước, cũng đầu năm thế kỷ trước, ta hiểu rất rõ rồi. Mặc dù lúc đó các phương tiện kỹ thuật hiện đại chưa có như bây giờ, như thể nói là những cái hệ đo mới như là AFM, Atomic Force Microscope, người ta có thể nhìn thấy các cấu trúc các cái nguyên tử sắp xếp trên bề mặt. Thế rồi là TEM, Transmission Electron Microscope, thì nó giúp chúng ta nhìn thấy những cái nguyên tử được sắp xếp. Bởi vì cái thang của TEM nó đến mức độ nano thì có thể nhìn thấy nguyên tử sắp xếp ở trong tinh thể. Thế nhưng mà người ta đã tìm thấy cái này từ rất lâu rồi. Thế thì bây giờ làm thế nào để từ lâu rồi người ta biết được cái cấu trúc tinh thể của vật rắn kết tinh? Thì lúc nữa khi mà học đến cái phần bạn đảo ta xin bày kỹ hơn. Nhưng bây giờ về mặt lý thuyết ấy, thì chúng ta xuất phát điểm là từ cái chỗ là các cái nguyên tử sắp xếp trật tự tuần hoàn. Thế thì chúng ta hãy coi mỗi một nguyên tử hay phân tử như là một chất điểm trong không gian. Bây giờ chúng ta đi sắp xếp các cái chất điểm đó và ta gọi nó là cái điểm mạng trong không gian một cách trật tự tuần hoàn. Sau đó tìm hiểu tính chất của nó. Như vậy thì cách tiếp cận về mặt lý thuyết là chúng ta chưa biết tinh thể thế nào, nhưng chúng ta hãy dựng lên một cái mạng tinh thể và ta gọi đó là mạng không gian, và tìm hiểu tất cả tính chất của mạng không gian đó. Đây là chúng ta đang đi làm cái việc đó. Tôi nhắc lại là hiện nay chúng ta đang trên con đường đi dựng lên một cái mạng không gian, chỉ với cái xuất phát điểm ban đầu là các nút mạng được sắp xếp trật tự tuần hoàn. Thế thôi, và xem là nếu trật tự tuần hoàn thỏa mãn các yếu tố đối phép đối xứng, yếu tố đối xứng thì có bao nhiêu kiểu trật tự tuần hoàn. Và chúng ta đã hình thành, và nếu các bạn đọc thì thấy rồi là khi phân các nhóm chỉ có mấy cái hệ tinh thể, 7 hệ tất cả. Và như vậy thì cái trật tự tuần hoàn đó là bị giới hạn. Và cũng trong cái việc mà tiếp cận như vậy thì chúng ta thấy điều rằng là vì cái tính trật tự tuần hoàn của mạng không gian, cho nên ta không nhất thiết phải đi tìm hiểu tất cả. Cái mạng không gian của nó là không giới hạn theo các chiều, đúng không? Và bởi vì nó trật tự tuần hoàn thì gì phải đi tìm hiểu tất cả. Như vậy thì chúng ta phải định nghĩa mạng không gian đó là chúng ta xây dựng các cái ô cơ sở, đúng không ạ? Và chúng ta trồng cái ô cơ sở đó theo 3 chiều thì chúng ta được mạng không gian. và có nhiều cách để chọn cái ô cơ sở. Thế thì các ô cơ sở khác nhau thì có tính chất đối xứng khác nhau, và chúng ta cũng đã học là các cái tính chất đối xứng của từng loại ô, và lúc nữa thì các bạn sẽ trình bày xem là các cái ô đó thì tính chất đối xứng của nó như thế nào, các yếu tố đối xứng làm sao, và tìm ra các cái thông tin đó. Thế thì đấy, chúng ta hiểu về cấu trúc tinh thể, cách tiếp cận của chúng ta như vậy. Chúng ta đi trên con đường là dựng lên một cái mạng không gian, và khi dựng được cái mạng không gian đó rồi thì chúng ta sẽ tiếp tục chứng minh là cái mạng không gian đó nếu thay cái nút mạng bằng một nguyên tử hoặc nhóm nguyên tử sau đó là phân tử thì chúng ta thu được mạng tinh thể. Và đây chính là cách tiếp cận khi chúng ta học trong cái học phần của lý chất xám này. Đấy, thế thì chúng ta đến chỗ này rồi, và nhắc lại là hiện nay chúng ta đang trên con đường tìm cách trả lời câu hỏi thứ hai là các nguyên tử sắp xếp trật tự tuần hoàn như thế nào ở trong tinh thể. Được chưa? Thế thì ôn lại như vậy để các bạn nhớ lại tất cả những nội dung chúng ta đã tìm hiểu trong chương 1, được không? Thế thì bây giờ hôm trước chúng ta đã xem đến đâu rồi? Đến đây đúng không? Nghĩa là chọn cái ô cơ sở. Thế thì khi mà học các cái tính chất đối xứng thì ở trong cái đối xứng thì có một yếu tố xứng là tịnh tiến, đúng không ạ? Thế nhưng mà thầy vừa trao đổi xong là chúng ta không tìm hiểu toàn bộ tinh thể hay là mạng không gian, mà chúng ta chỉ lấy cái ô, một cái đơn vị nhỏ nhất thôi nào để đại diện cho toàn bộ mạng không gian, để không cần thiết để tìm hiểu toàn bộ nó vì tính đối xứng. Thế thì lúc này chúng ta không thể dùng cái phép tịnh tiến nữa, vì tịnh tiến là dịch cái ô đi rồi, và như vậy chúng ta không xét yếu tố là tịnh tiến. Thế thì khi mà xét sau này xét ô mạng chúng ta biết rằng là chúng ta có quyền chọn cái ô cơ sở khác nhau, cơ sở cực khác nhau. Thế thì chọn như thế nào? Thì cuối cùng ta phải có một cái tiêu chí là chọn cái ô sao cho cái tính đối xứng cao nhất. Và như vậy thì để chọn ô tính đối xứng cao nhất thì về nguyên tắc nhất thì lúc nào chúng ta cũng chọn cái ô mà chỉ chứa một nút mạng. Cái này phải chứng minh là trước là ô đã chỉ chứa 4 mạng, vì mỗi một góc là 1/8 cho 8 ô. Nếu trong mạng hai chiều là 1/4 cho 4 ô, đúng không? Như vậy thực tế trong một ô chứa một nguyên tử. Và lúc nào chúng ta cũng chọn được một cái ô có chứa một nguyên tử trong một cái ô cơ sở. Được chưa? Thế thì cái việc gọi ô cơ sở sơ cấp ở trong tiếng Việt thì hơi lẫn lộn, nhưng tiếng Anh thì nó có rõ ràng ra cái tên đó là primitive và conventional. Primitive nó là chỉ có chứa một nguyên tử trong một ô cơ sở thôi. Thế còn conventional là có thể có nhiều hơn. Ví dụ như là cái hình bên phải này. Cái bản thân hình bên phải ta biết rằng là có 8 nguyên tử ở 8 góc, và mỗi một góc này hay một ô để chỉ chiếm 1/8 cái nguyên tử thôi. Và như vậy 1/8 cộng với nhân với 8 là có 1, và cộng một nguyên tử nằm ở giữa này. Tâm này nó chẳng chia sẻ cái ô nào cả. Như vậy chúng ta có 2 nguyên tử. Như vậy thì bản thân cái ô này cũng là cái ô mà chúng ta hoàn toàn có thể chọn chỉ có một nguyên tử trong số các. Chúng ta nhớ rằng ở dưới này có ô một nguyên tử nữa, và như vậy chúng ta nối nguyên tử này vào, như vậy thì vẫn là 8 nguyên tử. Và như vậy thì cái ô mà nối xuống cái này á cũng chỉ chứa một nguyên tử thôi. Thế nhưng tại sao chúng ta phải chọn ô chứa 2 nguyên tử trong một ô cơ sở thế này? Bởi vì để thế này thì cái tính đối xứng của nó sẽ cao nhất, và nó trở thành cái ô gọi là cubic, lập phương tâm khối. Và lúc nữa thì sẽ có nhóm trình bày tính đối xứng của cái ô mà có tính đối xứng cao nhất này. Và như vậy thì để đạt được mục tiêu là cái ô mà chúng ta lựa chọn, đấy, một cái ô đơn vị chúng ta lựa chọn có tính đối xứng cao nhất thì bắt buộc chúng ta phải chọn nhiều hơn một nguyên tử trong một ô, và tôi gọi đó là cái ô conventional, và nó là non-primitive. Được chưa? Ok, bây giờ thì đấy là cái nội dung chúng ta đã học và đã trao đổi rồi. Thế thì trong buổi hôm nay thì trước hết thì các bạn đã có những nhiệm vụ. Thầy sẽ tắt cái này để share cái nội dung mà phân công nhé. Đây, trước là cho buổi học thứ 2, buổi học thứ 3, đúng không ạ? Và như vậy thì có 5 nhóm, và mỗi nhóm đã có nhiệm vụ của mình rồi. Thế thì bây giờ từng nhóm sẽ trình bày để để xem là chúng ta đã chuẩn bị như thế nào. Và thứ nhất là chúng ta sẽ trình bày bằng tiếng Anh, đúng không ạ? Và nhóm 1, các nhóm đã sẵn sàng chưa? Giờ thì hỏi nhóm thứ nhất ạ. Nhóm thứ nhất thì ai sẽ trình bày ạ?
Nhóm em có 2 người trình bày ạ.
Ok. Trước khi trình bày thì bây giờ lớp trưởng hôm nay có mặt ở đây không? Lớp trưởng có mặt. Lớp trưởng gửi qua Zalo cho thầy cái danh sách của lớp được không ạ?
Dạ có.
Có danh sách không?
Dạ có.
Ok, thì em gửi qua Zalo để thầy sẽ sử dụng danh sách đấy để thích nốt những vấn đề thầy cần ghi trong đó nhé. Nào bây giờ nhóm số 1 bây giờ thầy sẽ stop share và thầy để cái quyền bây giờ thầy để quyền share screen và mời đại diện của nhóm 1 sẽ trình bày cái phần nhóm chuẩn bị.
Hello everyone, we are Group 1 and today we will have a presentation about the Miller index. So first I will introduce my team members. Our group has 5 members: Quách Thị Chi, Thẩm Vĩnh Đức, Lê Thị Thanh Huyền, me, Trịnh Việt Nam, and Nguyễn Thị Chỉ Trang. First, I will talk about the definition of Miller index. Miller index are used to specify direction and also planes. The direction and planes here they could be in the lattice or in the crystal. And the number of index is will match with the dimension of the lattice or the crystal. For example, in 1D, one-dimensional, we will have 1 index, and in 2-dimensional space, we will have 2 index, and the same for 3D and 4D and more. And next is the Miller index for direction. The Miller index for direction are really similar to the vector we have learned before. A vector R can passing from the origin to a lattice point can be written as R equal to R1A plus R2B plus R3C, where ABC is the basis vector on the 3 axis X, Y, Z. And here we will have the Miller index R1, R2, R3. The fraction in Miller index are eliminated by multiplying all components by their common denominator. For example, we have a vector 1 over 4, 1 over 2, then we'll have the Miller index that 4, 3, 2. Yes, example. In here we have the vectors 4, minus 2. Then the Miller index will be 4 minus. For the minus side, we have a bar over the number 2. For the minus sign, like we have learned in the imaging number. And here, the index represents a set of all such parallel vectors. They all have the same Miller index for 2 bar. You can see they all have the same direction as the first vector. And next, Đức will talk about the Miller index for planes and how to find them.
Yes, I will talk about the Miller index the plane. And after the definition, we could find the Miller index for plane by 3 steps. Step 1 is identify the plane intercept on the x, y, and z axis. 2. We specify the intercept. Excuse me, this I could not hear you clearly.
Yes. So can I change my device?
Yeah. Okay. Sure.
So, can you wait me for screen?
Okay.
Okay. I just changed my device. So
it should be better. Yeah. Okay. Please.
Yes, thank you. I will talk again. After the definition of the Miller index, I will present the Miller index for plane and how to find them. We could find the Miller index for planes by 3 steps. Step 1, we should identify the plane intercepts on the x, y, and z axis. And step 2, we specify the intercept in the fraction no coordinate. And step 3, we take the reciprocals of the fraction intercept. So that in the Miller indices for plane, we have to enter the reciprocal space. So what is the reciprocal space? The reciprocal space means you take the inverse of whatever point, like the inverse of 1 is still 1, and the inverse of 2 is 1 over 2. So that the inverse of 0 is infinity. We come to the first step. We consider the plane in pink, which is one of an infinite number of parallel plane H, a consistent distance A away from the origin, is the purple plane. And here, we concentrate to the purple plane. The plane intersects the x-axis at the point A. And as you can see for the plane Y and plane Z, the plane is parallel to the OY and OZ. So that the intercept of Y and Z is infinity. And after that, we take the reciprocal to three factor. Yes? And we can find the Miller index is 1, 0, 0. And for the green space, is the upper plane. You can see that the plane is parallel to the OX and the OY. So first factor is still infinity, and they cut the OZ, so the factor SZ is 1. And after that, you take the reciprocal and have the Miller index is 0, 0, 1. Similar to the yellow phase, you can find the Miller index is 0, 1, 0. So we come to the first example.
Now I will talk about the example, so you guys will understand better how to find the Miller index for the plane. So first, here we have look at the purple plane here. And what is the Miller index of this plane? First, we see that the plane intersects with the x-axis at the point A00 and intersects the y-axis at the point 0, A0, but is parallel to the z-axis. So we can call it intersects to the z-axis at infinity. So we have the intercept 1, 1, infinity, and take the reciprocal. 1 over 1 is 1, 1 over 1 is 1, and 1 over infinity is 0. So the Miller index of the plane is 1, 1, 0. Move to the example 2. We have another plane, but is intersect with all three axes. So can anyone answer what is the Miller index of this plane? Can anyone? Maybe Hiếu, can you do the Miller index of this plane?
Okay. I think that this plane is intersect both of three axes. So the first of all, we will have that it will intersect the x at 1, intersect y as 0, 1, and intersect the z as 0, 0, 1. So we will have that 1, 1, 1. And so after we take the reciprocal factor, we will reduce it into the 1, 1, 1, and the final Miller index for the planes is 1, 1, 1. Yeah, I think so.
That's true. Thank you. And that is the reciprocal for this plane because it intersects all three axes at point 1, 1, 1. So we take the reciprocal by we take 1 divide each number here, and we have the Miller index 1, 1, 1. So the final example. Here we have the plane, but it intersects the x-axis at 1 over 2a 0, 0, and y-axis at 0, a 0, and the z-axis as infinity. So we see that we have the intercept 1 over 2, 1, and sorry, here is maybe the infinity. So we take the reciprocal by 1 divided to 1 over 2, we have 2, 1 over 1 is 1, and 1 over infinity is 0. So here we have the Miller index is 2, 1, 0. And then we'll talk about the importance of Miller index.
Okay, for the last part, we come to the importance of Miller indices. In material science, it is important to have a notation system for atomic planes since these planes influence the optical properties, the reactivities, the surface tension, and the final is the dislocations. And I would like to talk more about the Miller indices for plane. As you know that the zero in the Miller indices is represent that the plane is parallel to the corresponding axis. And according to the Miller index for directions, all parallel planes have the same Miller indices. You can find it more after this presentation by contacting to me. And that is our presentation about the Miller indices and how to find them in direction and planes. If you have some comment, please. We would like your comment about our presentation.
Okay, so thank you, Lam and Dick. On behalf of the first group, present the first topic today about the Miller index for direction and plane, right? Okay, so it's now time for any comment and question, please. So everyone, make sure that's clear about how to define the Miller index for direction and also for planes. Are you sure that? And if not, if you have any questions to make this more clear, please. So you can raise your hand or you just turn on the microphone and just give a question. Okay, so waiting for other question. Can you, Dick or now, please can you go back to the slide that show how to define the Miller index for direction? Okay, you can start with the slide number 5. Okay, for example, in this slide, everyone can look at the, for example, the first figure, and in the first image, not a figure, right? This is in the left image. Can you see that the author wants to determine the direction they call below is 4 minus 2. Okay, so the question is that how can you define the two number 4 and minus 2? The question is how?
Well, the number 4 and minus 2 is we define it from the distance from the origin to the point we to the distance from the origin to the point we are working with. For example, this point and here is the origin, so we draw the vectors, and we will turn the vector into two vectors, on the z x-axis and y-axis. So on the x-axis, we know that the vector is 4a, and on the y-axis, vector is 2b. So we will know the numbers of the vector is 4 and -2.
Okay, so any other one have comment on the way to determine the mirror indices of this direction? Okay, so I think it helps you following the procedure. Okay, so the direction, of course, actually direction here is to determine the light, right? Direction or light. So it will be for that to determine the light, you should point out the 2 points belong to this line. It's one way, right? And for direction, you have the basis vectors. So for example, here in this case, now you have to point out the mirror index for this direction, from 0 to the wanted point. You have to, the first step in procedure, you have to take the projection of this line to the 2 axes, basis axis, right? So the projection of this line to the x-axis, you have the 4a, and projection of this line to the y-axis, you have -2. So if in case you have the 3 dimensions, you have to take the projection to 3 basis axis, right? So this is going to be more clear. How can we define the number 4 or -2? Is it clear?
Yes.
Okay. You didn't have any example of the 3-dimensional, because the variation it takes the example of only 2, right? For the 2-dimensionals. How about 3-dimensional? You have any example?
We don't have the example for the direction in 3-dimensional, but I think it's the same as the vector we all learned before, so I think everyone is understand.
Anyone have a question for this feedback? Please. It is not clear, so you should have a question, so that I can explain in more detail.
But we don't have, we didn't have the example for 3-dimension yet.
Okay, but I mean, other member, do you have any question? How to determine the mirror in this direction, please? Okay, keep going. Okay, so you see that the mirror in this direction is 4 2 minus. Do you think it's correct or not? And why?
Can you repeat the question?
Yeah, I mean that you put the number in the square brackets 4 2 minus, right? So 4 2 minus is this the mirror in this positive direction? Is this correct?
Yes, I think it's the direction. It's the Miller index for this direction.
Okay, for example, it looks like this. Okay, so I just stop the line at this point. Can you see that? Sorry, I could not show the point in this slide. So can you send your slide by Zalo? So I can show it from my slide.
Yeah,
This slide is more clear. Since it is the download is take time. Okay, you can wait for a moment. So this is okay now. Okay. Everyone can see the slide group 1 from my computer, right?
Yes, we can see.
Okay, sure. Let's start with this slide number 5. Okay, so the group 1 defines this direction. Okay, this direction with the similar index 4, 2, minus. And I think that there's some mistake here because the procedure of finding the similar index for direction. First of all, you have to take the projection of this direction of this vector to the two basis vector. In this case, we have the 4a and 2b, this minus, right? And after that, you have to find the minimum integer number to describe this relationship. Here we have the 4, 2. So the smallest integer number to define this direction should be 2, 1, minus. Because if you take this vector, stop at this point. You can see that? It takes its vector stop at this point. So it takes the projection, you have 2, right? 2a and minus 1b. And you have relationship of the 2 minus 1. And you see that because the mean in this so is the direction. And you have the same direction, right? You should have the same direction because it stays in one direction, this different vector. You understand what I mean? So the procedure of finding the mirror index, you should take the projection of this vector. Then you have to find the smallest integer number to describe this relationship. So the smallest integer number in this case should be 2, 1. Okay? And you have to do the same for other procedure to find the mirror index. In my slide, I upload on the CSV. I show you clearly the step by step to find the mirror index for direction. Okay? Do you understand my meaning?
Yes, I understand now.
Okay. So after this presentation, I think that's group number 1. So please check again, and you can modify the slide and send it back to me. Okay, and later I will upload this slide on the CSV board so other students can access it. Okay. So now I'm going to the some mirror index for planes. I think that you make a lot of the example. Okay, a lot of example how to define. But first of all, I think that we have to make sure with the procedure. Otherwise, the other student could not understand how to find the mirror in this plane. Once again, what's the purpose of the mirror in this plane? Because this is one way to define the plane. I don't know, in high school, right? In high school, you study about planes already. And if you want to tell other student or teacher about the plane you want to say, you have different way, right? You can point out the 3 points in this plane, not collinear. Okay, 3 non-collinear points in this plane, so other people can understand what plane you want to talk about. Okay, and today we have other way to define the planes. This is a mirror index. So using mirror index, you can tell the other people understand the plane that you want to say about. So how to define this? So you have to follow the step. First, you find the intercept of the plane on the 3 basis vector, x, y, and z axis, right? And specify intercept in fractional coordinates. Take the reciprocal of the fractional intercept. I think it's not enough. After take the reciprocal of the fractional intercept, you have to find the 3 smallest integer number, okay, to describe this relationship. You understand? Because after you take the reciprocal, it's not integer at all. So you have to find the smallest integer number to describe this relationship. Okay? And you put this 3 smallest integer in the bracket. So we call it the mirror index. And the question arises, how to find the smallest integer number? I think the people call in English is reduce the fraction into the common denominator. In Vietnamese is quy đồng mẫu số, right? Okay, so you have to take this more step to find the mirror index. he does that, but he could not say is clearly here because you take the example of very simple equation, or you look at this integer. See, you have to intercept up to 1 half, right? Half 1 0. So 3 smallest integer number to describe this relationship should be 2 1 0, right? So actually it takes what I said before, middle also. And to find the 3 smallest integer number to describe this relationship, right? So you should describe it more clearly, so you have different steps. Yeah, take reciprocal and then reduce the fraction into the common denominator to find the smallest integer number to describe this relationship, then put it in the brackets. Once again, the student for group 1 also want to say about the what the importance of Miller English, but in some time, because of the way or procedure to find the Miller English for plane, so if the plane parallel to each other, they should have the same mirror image. So actually, the mirror image to describe the set of planes that parallel to each other. Okay, they also have the special the set of plane in the mirror by the square brackets. Okay, and they also put the some plane with special property of the rotation with the curly brackets. So you have to define why sometimes they put the curly brackets and also the square bracket for mirror image. What is this? In the slide I upload on CSV, I describe this more clearly. Okay. Okay, this is the time, but anyway, we have to finish the first presentation of the group 1 first. So, anyone have any more questions, please? Is anyone anything not clear? So let's raise our hand or. Okay, so there's question. If the reciprocal is 1 third, 1 half, so what's the mirror image? Okay, so this question, anyone can, group 1 can answer this question? Group 1, can you see this the question?
Yes, I
can you see
it? Yeah.
Can you see this?
Yes, I can see it now.
Okay.
If the reciprocal is 1/3, 1/2, and 1/2, we take reciprocal, and we have the Miller index is 3, 2, 2.
See, this is a mistake. This is a problem that I said before. So 3, 2, 2 is not correct in this case. So this is a problem that I said before. So if you don't know how to define the Miller index, because after take the reciprocal, you have to find the smallest integer to describe the relationship. Okay? You understand? Okay, so reciprocal is the Okay, so for this question first, this means that the plane intersect with the x, y, z at the position of the 3A, right? 2B and 2C, right? This is the intersect of plane with the 3 axes. Is this correct? So it takes a reciprocal. Okay, this first, the intersect of the plane with the 3 axes, and the second, it takes the reciprocal of the 2 is 1 3, 1 half, and half for reciprocal. And the third step, you have to find the you have to take the reduce the question to a common denominator. So in Vietnamese is the or all you have to find the 3 smallest integer to describe the relationship. What relationship? 1 3, 1 half, and 1 half, right? And to reduce the fraction to a common denominator, you have to take the 1 3 equal 1 half, equal 1 half. It takes the common denominator is 6, right? Is 6. So you have the 3. You have the 3 relationship like 2 over 6, 3, 2 over 6, 3 over 6, and 3 over 6. So this means that you have the 3 number, small integer number is the 2, 3, and 3. So the mirror image should be 3, 2, and 3, right? So it puts 3 number on the bracket. So this is the mirror image for this plane. Do you understand? So 23 is the mirror image for this plane.
Yes, I misunderstood the question. So he says reciprocal, but I thought this was the intersect with 3 axes. Or I thought it was 3 2 2.
Okay. So do you understand how to define the mirror image? So thank you. Who gives this question? Okay. Anyway, I think it's a good question for everyone to define how to utilize the mirror image for planes. Okay. So is this clear? Is this clear?
Yes, this is clear.
Okay. Okay, so this for plane. But how to find the mirror image for direction? So what difference between the mirror image of direction and plane? So group 1 can you answer this question? I mean the procedure to find the mirror image for direction and plane. What's different?
With the direction for the mirror image for direction, we do not take the reciprocal after for the plane we need to find the intersect with 3 axes and we take the reciprocal, but for the direction we just take the projection of the vector in 3 axes, and we take and we skip the second step. We don't take reciprocal, but we reduce the fraction to common denominators.
Okay, right. Okay, thank you. So remember, if do not do the same procedure for on the way to find this mirror index for direction. Because in the mirror index direction, the first step, you have to find the projection of the direction onto direction. Okay? And you go to the third step, just find the smallest integer number to describe the relationship. That's all. You do not take the second step to take the reciprocal. Okay? Remember. So this is two different way of determining the mirror index for direction and for length. Okay, so everything is clear? Any other question? Any other question, please? Everyone clear that? Okay, you are feel confident to find the mirror index of direction and place at all? Okay, it's no more question. I think it's okay. Okay, so thank you, group number one. You prepare the slide is really attractive and but anyway, they are still not clear in the procedure of finding the mirror index for most planes and direction. So please, group number one, you modify the slide and send it back to me before upload it on CSV for other people can access it. Okay. Okay. Once again, thank you, group one, and we have. Well, it's 9:06, so we have 5 minutes break. Okay. Thank you. Okay. Em lên lớp cái xong rồi em lên nghỉ giải lao đấy ạ. Vâng, thế ngồi đi ạ. Bây giờ thầy sẽ mời tiếp nhóm tiếp theo nhỉ. Bây giờ nhóm tiếp theo là nhóm số 2. Thì nhóm số 2 là thì biết là số 2 là ai đấy? Nhóm số 2 là bạn nào đã chuẩn bị đấy?
Em ạ, nhóm 2 em.
Nhóm số 2 em đúng không? Bây giờ thầy có để quyền share screen rồi. Bây giờ mời bạn giới thiệu nhóm và trình bày.
Okay, hello everybody. My group is group 2 and our team member are Nguyễn Mạnh Hiếu, Phạm Lê Anh, Nguyễn Ngọc Mai, Phạm Tuấn Kiệt and Nguyễn Thu Thủy. Yes. And today we will present about the symmetry elements of monoclinic and orthohommic of crystal system. We can see that in this table we have all the property of the monoclinic and all the properties of orthohommic. The final columns is they call that is the gray base. This the last column here is the gray base lattice. This is the gray base lattice. This is the elements. This is the symmetry elements. Is the thing we were talking about today. Is this column. This column is the length of crystal system. This is the length of crystal system. This is the angle between three basis vectors, and this is the we can say this is the basis vectors or the length of basis vector. We can see in this table. Okay, first of all, I will talk about the monoclinic. This symmetry, we can see that in here. This first symmetry elements of monoclinic is C2. Okay, so what is C2? So the C2 here means that its rotational order is N2, and the rotational order is N from the rotational order N equal to, and due to the definitions, N2 means that this will rotate about 360 divided by 2 equal to 180. As you can see, it means that the monoclinic can rotate 118 around this rotational axis to become or to come back to its original form, and we call that this is C2 is the rotational symmetry, because it rotates about 180 angle to come back to its original form, and thus the C2 means that it has the rotational order 2. From that, combined with the definitions, we know that the angle of rotational symmetry is 118, and after rotated 118 around this rotational axis, it will come back to its original form. And the second symmetry element is sigma 8. The sigma 8, due to the definitions, is defined as the symmetry plane that is perpendicular to the rotational axis. Yes, and sigma 8 also represent for the reflections. This also represent for the reflections symmetry. Yes. Yes, here is the blue plane. We can see that sigma 8 is represent for the reflection symmetry, and because it's the reflection symmetry, so it needs to have a plane that divided the object into two equal parts that have the same shape and same side. So sigma 8 here is the plane, the symmetry plane that perpendicular to the rotational axis. As mentioned before, we can see that the rotational axis go through this center of monoclinic. So the symmetry plane or the reflection symmetry plane is perpendicular to the rotational axis, and this plane is divided the monoclinic into two separated parts which have the same shape and same side. And sigma 8 also represent for the reflection symmetry. And finally, we talk about the Breivik lattice in the last column of the table, as I mentioned before. The monoclinic have two Breivik lattices in simple and space centers. Yeah. And we can see that here the three basic vectors are different, mean that their length may be different. For example, I have relative. Yeah. A3, this should be A1, this should be A2. Alpha is the angle between A1 and A2. We can see that A1, A2 is 90 degrees. This is alpha. Gamma is the angle between A1 and A3. So it should be this. This should be gamma. And finally, the beta is the angle between A2 and A3. So this angle should be different from 90 degrees. You can see. Now for the orthorhombic, its rotational order still be the same as monoclinic. It means that n still equal to 2. So the rotational angle is still 180. Right. And the difference here is the monoclinic. The monoclinic, as I said before, is only have C2, but for orthorhombic, it have 3 C2. 3 C2 means that it have the 3 rotational symmetry axis. We can see here. It can rotate about this axis 180 to become back to its original form, or it can rotate this axis, or it can also rotate around this axis. It can rotate around these 3 axes about 180 degree to come back to its original form. That is the difference between the mono and orthorhombic. Mono only have 1 axis of C2, but orthorhombic have 3 axes, 3 rotational symmetry axis. Yes. And also for the sigma 8, as I mentioned before, sigma 8 is the reflection symmetry plane, and the 8 means that is perpendicular to the rotational axis. And in here, because we have the 3 rotational axis, so it's also have the 3 symmetry reflections planes that are perpendicular to the axis. You can see in here is the green, 1 plane, 2 plane, and the 3 plane. These 3 plane divided this cubic into 2 separated parts with the same shape and same size. Okay, and remember that 8 means that the symmetry plane is perpendicular to the rotational axis. It also have another thing like the sigma v and some kind that I don't remember. But remember that 8 is the plane that perpendicular to the rotational axis and divide the object into 2 separated parts that's equally in shape and size. We can say that this is the reflection symmetry plane. And for orthorhombic, we have 4 Bravais lattice. That is a simple, base centeredness, body centeredness, and face centeredness cubic. And you can see here that the 3 basic vectors are still different, mean that maybe their length are different. For example, I will take A3, A1, and A2. And the 3 angles of these 3 basic vectors are all equal to the 90 degrees. You can see on the figure I have drawn here. Okay, so our presentation here is ends. Thank you for listening. And any questions so far? Anybody? Any questions so far?
Yeah, so thank you for the presentation. Okay, so from now on, we are going to find the symmetry property of different Zilli cell. Okay, different Zilli cell have different symmetry, or it have different symmetry elements. So you are required to find the symmetry element of the different cell. So the first group will present the how they find the symmetry element and they try to prove that if we apply this symmetry element, the cell is invariant, okay? Or if you close your eyes, you don't see what they have done after they apply the symmetry element. The cell looks the same that before. Okay, so let's try in this way. And the first group have the find all the symmetry elements for monoclinic and orthorhombic. So now at this time for other students, if you have any comment or question or anything is not clear, so let's ask the author. So we might discuss more. Okay, please, any question? Okay, so remember you have different symmetry operation. You have the rotation, you have the reflection. You see, for reflection you have to find the plane, right? For rotation you have to find the axis of rotation. And you also have to find the inversion point. So whenever you find the point for inversion, you find the axis for rotation, you can find the plane for reflection. So that's all the operation of the symmetry for the cell. As I said before, you also have the vector for the whole lattice, but now you consider only the cell. So there are only 3 symmetry operator, and the first group have find all the symmetry elements. And any questions that is unclear of the any operator of symmetries, you can give the question or any more comment for this. Please. Everything clear? Okay, so I ask the question, can you go back to slide number 2? Okay, so in the last rows, so for the monoplate, it has P and C. Can you explain what's different between P and C?
Yes. PC here is the notation for the previous lattice. We can see that P is stand for simple cubic and C is stand for base center cubic. We can see that P, we have a cubic that we only have that we can see that in the we can see that this have no, this is the primitive cell. If we see this is primitive cell because it only have the 4 lattice point as the corner. But for the base center C, it stands for base center cubic. We can see that it also have a lattice point at the middle of this unit cell. So this, I think that is the non-primitive cell and this is primitive cell. That is the difference.
Okay, thank you. So, okay, go back to the slide number 2. Can you go back to slide number 2, please? Okay, look at this table. You're right that every system, monoplates, orthorhombic, and lateral, you see that the first letter also P. So this means that every system has primitive cell. In primitive cell, I said before, it contains only 1 lattice point. Okay, only 1 lattice point. But they have some other conventional cell. Conventional cell, this means they add more lattice point in order to have highest symmetry available for this system. So they have the base centers. And for orthorhombic, they also have primitive denoted by P and base center denoted by C. And also on, okay? So this means that it's a conventional unit cell. More lattice point as in order to have highest symmetry, okay? Okay, thank you. So, any more questions, please? Anything clear? Okay, if everything clear, so Thank you, group number 2, and we are going to the group number 3. Group number 3, are you ready?
Yeah, we're ready.
Okay. So can you show the slide and please show the preparation.
Do you see the screen?
Okay, sure.
Hi everyone. It's the presentation of Group 3, and my name is Dr. Lee. So today I will talk about the symmetry element of tetragonal system. One definition. The definition of the tetragonal system. In the tetragonal system is one of the 7 crystal systems, and the tetragonal system lattice results from stretching a cubic lattice along one of its lattice vectors, so that the cube becomes a rectangular prism with a square base A by A and the height C, and C is the different from A. Is a gravity lattice in 2 dimensions. The gravity lattice of the tetragonal system is the square, and in 3-dimensional, there are 2 tetragonal gravity lattice. Is the simple tetragonal and the center tetragonal. So I move on to the property, the symmetry of the tetragonal system, and I will give the example is the cornea system. The cornea is a polymorphic material occurring in 3 temperature-dependent forms. It's a monoclinic, a tetragonal, and a cubic. And I will talk about the tetragonal form of the zirconia system. So I will find the rotational symmetry of the tetragonal system. The simple CN. To find the acid of symmetry in zirconia's crystal, I hold we are seeing that if I hold the zircon crystal along C axis in the future and rotate it by 360 degrees, do you think how many times the rectangular and the triangular will repeat if I rotate it by 360 degrees? Somebody can tell me? If I rotate it by 360 degrees, the rectangular and the triangular will repeat how many times? Mạnh Hiếu?
I think that if we rotate it about 360, it will have 4 times to come back to its original form.
Yeah. So I can call it is one acid of tetrasymmetry, and it's the one acid of fourfold tetrasymmetry. We can easily see that if I rotate it by 360 degrees, the system will repeat 4 times. The shape of the system will repeat 4 times, and it not only have the fourfold symmetry, it have the four axis of twofold symmetry. To define the four axis of twofold symmetry, firstly, I hold the crystal along 2A, CS, and AE, and rotate the crystal by 360 degrees, and you can observe the pyramid form is repeated 2 times, and I call it the one axis of twofold symmetry. And step 2, if I repeat the same exercise, I hold the crystal along the A, PB, FB, and ZD, and rotate at angle of 360 degrees, and you will observe that pyramid form will repeat 2 times. And repeat, we can observe the 4 axes of twofold symmetry in zirconia system. It's an all axis of zirconia system. It includes 1 axis of fourfold and 4 axis of twofold. It's a one axis of C4 and 4 axis of C2. And I will talk about the reflection symmetry, also called the mirror plane. The plane of symmetry is a plane which divides the crystal into 2 similar halves or similarly placed halves. And the plane will divide the system into 2 parts. Similar. And the zirconia system will have the 5 plane. 5 mirror plane. The 5 mirror plane we are called as the reflection symmetry. It have 3 axial plane and 2 diagonal plane. You see in the picture we have 5 plane. It means that each plane will divide the system into 2 parts equally. Continue. I will talk about the inversion symmetry. The inversion symmetry is described by the coordinate transformation. Vector r prime equal to the vector minus r. So inversion move every atom in the system to the another position in the crystal. The O and mu position of the atom lie upon the line, and the middle of which is the center of inversion. And to have the inversion symmetry, all the phases of the crystal must occur in a parallel pair for crystal to possess a center of symmetry. And to define the inversion, to find the center of inversion of the zirconia system, we connect the point
cái đỉnh pyramid, the up pyramid and down pyramid, and the middle of the line it is the center of inversion. So the zirconia system will have one inversion symmetry. This O. Yeah. And the and my presentation is over. Do you have any question?
Okay, thank you. So I think there will be a lot of questions about the how to define the symmetry element for this system. Everyone clear with the presentation of the group number 3? And if not, so we can have the question, please. Can you go back to the first slide? Okay, can you go back to the first slide, please?
Yeah. Yes.
So what's the system you are working with?
It's the tetragonal system.
Okay, so the tetragonal system, what's the property of this system?
The system have the standard unit length of H. It have 3 H is A1, A2, and C, and the unit length of H is A1, A2 is equal, and C is different from A1 and A2. And SO is a 90 degree between A1, A2 and A1C and A2C.
Okay, so you should remember that we are now not consider the real crystal. We construct the space lattice, okay, and we take the limit cell of space lattice to find the symmetry property. Symmetry property, or other way, we find the symmetry elements. And it proves that when we apply this symmetry element, the limit cell of this system is invariant. Okay? So, but in this example, you took the example of real crystal. Real crystal is another story. It's not easy for you to see the symmetry element of the real crystal. Later we will see. So in this case, it should be better if you just take the simple unit cell of the tetragonal system and you try to prove that when you apply this symmetry element, the cell is keep invariant. So this is easier for other students to understand, okay? You say that it has the rotation symmetry element, so you try to prove by applying this rotation. You have to point out where is the rotation axis, right? And you apply this rotation symmetry, the lattice or the cell is keep invariant. So this is the point. It's easier for you. If you took on the real crystal and try to prove that you apply this symmetry element, it's really hard for even me to keep up the way the axis and how to apply it is a Pythagorean system or not, right? This is my comment. How about other students? Do they have any comment on this? Or if you can get all the thing clear from the presentation of the group number 3. Okay, so that I say again that it should be better if it takes the very simple Pythagorean system, okay, and try to find where is the what's the symmetry elements. It is rotation. You just show the axis. Okay, this axis like the reverse group just saw before. This axis, and if you rotate, the system keeps invariant, and it shows the plane. Okay, so just draw the plane, and you prove that if you take the reflection, the cell keep invariant. Okay, so this means that you have to solve all the element, symmetry element, and you prove that when you apply this symmetry element, the cell keep invariant. So this is the requirement of this for easier for other students to understand. Okay? So my suggestion is that the group should prepare the present again. Following that, okay, take very simple Pythagorean system and try to find the symmetry element, and denote the axis for rotation, denote the plane for reflection, okay, and define the point for inversion. So that's all you need, okay. Yes, if you find from reference that there are some real crystals have the Pythagorean, and they also try to show the symmetry element. But now it's not the point. It's really hard for other people to understand this thing, okay? So is it okay with you? Group number?
I think it's okay. Yeah.
Okay, so thank you. So on again. So please try to work on the Pythagorean this cell. It's easier for you to show the other people all the symmetry element, okay? So send it back to me. Okay. So I think okay, thank you. So I think we are looking for the presentation of the group number 4. Yes. So okay. So group number 4, are you ready? So who will be the presenter of the group number 4?
The language of those with slide.
Okay.
Today, my group will talk about define the symmetry element of cubic system. My group head by member Hoàng Thị Như Quỳnh, Nguyễn Huyền Anh, Lê Thị Ngọc Diệp, Lê Minh Hằng, em Hoàng Vũ Quỳnh. About the content, firstly, is introduction. Second, center of symmetry and axis of symmetry and plane of symmetry. About introduction, Similarly, or exact correspondence in the crystal called crystal symmetry, it is decided by various symmetry elements. Symmetry elements included center, axis, and plane of symmetry. About center of symmetry, let's consider a Q as shown in the figure here. If the body centered point is considered and the body diagonal are drawn to its diagonal connect identical related points located at equal distance and in opposite direction from this point. This point acts as a point marrow, which generates the second lattice at an equal distance in opposite direction. Also, therefore this point is called the center of symmetry or inversion point. So center of symmetry can be divided in an imaginary point in the crystal, but any line drawn to it intersects the surface of the crystal at equal distance on either side. It is equivalent to the reflection through a point. Thus, for a cubic crystal, inversion point is located at the center.
Now we are going to axis of symmetry. Look at the picture. You can see if a Q is rotated about a vertical axis, then to complete the rotation of 360 degrees, we have to rotate the Q through 90 degrees. We can see here in every rotation of 90 degrees. Is it not possible to distinguish the Q from its congruent position? See, the position of the front face is changing, so in one complete revolution of 360 degrees. There are found to be 4 positions of the Q, which are coincident with the original position. Or in other words, we can say that each rotation of 90 degrees brings the Q into self-coincidence or in congruent position. So this rotation axis is an axis of symmetry. Axis of symmetry can be defined as a line about which the crystal may be rotated, such that after a definite angular rotation about this axis, the crystal comes into a congruent position. So now, in general, if a rotation through an angle of 2 pi over n radians or 360 by n degrees about an axis brings a figure into a congruent position, the axis is called an infold axis of symmetry. Now let's consider different number of folds. First, consider n equal to 1. The crystal is rotated through 360 degrees to achieve the self-coincidence. And in that case, the axis is known to be identity axis, and its crystal possesses an infinite number of sub-axes. Now consider n equal to 2. So for this crystal has to be rotated through 180 degrees to achieve the self-coincidence, and in that case, the axis is known to be a diagonal axis. If n equal to 3, the axis is called a triad axis, and the crystal has to be rotated through 120 degrees. For n equal to 4, the angle of rotation has to be 90 degrees, and the axis is termed as tetrad axis. Similarly, if the number of folds is equal to 6, the corresponding angle its rotation is 60 degrees, and in that case, the axis is called hexaxis. And as we have discussed earlier, it is found that the crystallized solids show only 1, 2, 3, 4, and 6-fold symmetry. They don't show 5-fold or any symmetry axis higher than 6. You can remember this reason for that. The fact is a crystal is not just a solid body, but it is one in which the atoms and molecules are internally arranged in a very regular and periodic fashion in three-dimensional pattern. Consequently, identical repetition of a unit can take place only when they consider 1, 2, 3, 4, and 6-fold axes. In view with this discussion, the cubic crystal possesses 3 axes of symmetry. So for 2-fold symmetry, the crystal is rotated through 180 degrees. Here you can see the rotation of 180 degrees shows the position of crystal as shown in the right figure. And the second rotation of 180 degrees achieves the self-coincident position of crystal. 2 rotations we have to attack. Therefore, 2-fold symmetry and axis is called a diaxis. A line which is join the middle points and central points of a pair of opposite parallel edges. The provide a diaxis, so you can find how many diaxes will be there in a cubic system. And there are 12 each in the cube, and the number of diaxes is 26. Now consider 3-fold symmetry. The crystal is rotated through 120 degrees. Here we can see the train in the position of the cube with rotation of 120 degrees. So by total rotation of 120 degrees, the cube achieves the self-coincident position. Hence, it's called as 3-fold symmetry, and the axis is known as a triaxis. So a line which joins the corner point of a pair of opposite parallel edges is known as triaxis. You can find how many triaxis will be in the cubic system. And here there are 4 diagonals in a cube, and the number of triaxis will be like this. For 4-fold symmetry of crystal is rotated through 90 degrees. Here we can see the train in the position of the cube. With every rotation of 90 degrees, so by 4th rotation of 90 degrees, the cube achieves the self-coincident position. This is called a 4-fold symmetry. Tetraaxis, a line which joins the center of pair of opposite parallel face, provides a tetraaxis, so we can find how many tetraaxis will be there. And here there are 1 normal to each pair of parallel faces. And hence the number of tetraaxis is 3, 6 dias, 4 triads, 3 tetrads. So there are total 13 axes of symmetry in a cube.
Now we are going to the end of symmetry. Let us see the co-symmetric element that is a plane of symmetry considered a cube, and now consider a plane in the middle of the cube and which is parallel to one of the parts of opposite phase. If in the plane middle and one half of crystal is cut and removed the plane from image of that half of the crystal. In this just means if we reflect one half of crystal in the plane of the image will coincide with the other half. Therefore, the plane is called a plane of symmetry. Or mirror plane. So now we can define that when an imaginary plane can divide the crystal into two equal parts, such as each part is the exact mirror image of the other, then the crystal is said to have a plane of symmetry. So we have three sub-planes of symmetry which are parallel to the face of the cube. 3. And thus we have 6 diagonal mirror planes in the cube are shown in the figure, which is formed by a path of opposite parallel edge. So in the end, it may be noted that the full crystallographic system of the cubic crystal comprised of the following 23 elements of symmetry, one center of symmetry, then 30 axes of symmetry, which consists of 6 dial axes, 4 trial, and 9 planes of symmetry, of which 3 are parallel planes of symmetry and 6 are diagonal planes of symmetry. Therefore, total symmetric elements in the cube equal 33. 23. Thank you for listening.
Okay, so thank you, group number 4. I think you prepare the presentation very good, and I think I do not remember, but the 3 of you have tried to present, right? So I suggest other group as more member to present, so you can practice English more, okay? And I think that you try to explain clearly each element, symmetry element, to determine the rotation symmetry. So you show the axis, right? For inversion, you show the point. For the inflection, you show the plane. I think everything is clear. And for cubic system, it's very easy to find the symmetry element because it has the highest symmetry among all the system. Okay? So any question, please? Anything clear? Okay, so the question can go to the slide number 11. Can you go back to the slide 11, please? Yes. Okay. Here it's very good that you show the rotation. It's a 2-fold, right? When you turn 180 degrees, so the cell will be invariant or go back to the initial position. Okay, so but it's shown in the last in the corner. right corner is the last one. I think that the 2 points to define the line is not in the center of the egg, right? Is it correct? Yes? Is it correct? Is the rotation of the 2 force? Can you explain more detail? Okay, look at the cell as a corner. Can you send this slide to me by Zalo? So from my side, it's easier to. Okay. Okay. Before. Okay, now I can send this. What is this here? Okay, everyone can see this? Now go to slide number 11. Okay, so look at this. As I said before, that group number 4 try to show you all the elements, matching element. For example, now they try to show the element of the 2 force or C2. Okay, so C2 just means when you rotate the tip by 180. The shape of the tip invariant, but I consider this one. So everyone here, you try to explain that it's the line or rotation axis is connected by we call it the middle of the egg, right? But it seems to me it's not in the middle of the edge. So is it correct for this axis? Do you understand what I mean? So I think that you have to define exactly the position of this axis again. I think that is not correct. That the rotation axis should connect 2 points between the middle of the opposition edge of the cube. Okay, so that's the only one point. So we try to draw this again to make it clear for this figure only. Okay. So do you get this? Group number 4. I could not hear any response from group number 4. Is this clear now?
Yes.
Okay. Any other question or comment? Okay, so if not, so we go to the final group. Sorry if it's we have to extend the lecture today might be after 11, but we still have one more group to present. So group number 5, the final one. I'm ready to show the slide. Okay, so group number 5 please.
Dạ, rồi em chuẩn bị.
Okay.
Hello everyone. Today our group 5 will be presenting to you the robot system of symmetries. Our group has 5 members: Nguyễn Nhật Hà, Hoàng Mai Anh, Nguyễn Hồng Nhung, Vũ Long Thành và em Nguyễn Minh Chỉ. We have in our presentation that first we will define the robot system, and after that we will define the symmetry of the robot system. First I'm going to talk about the definition of robot. Robot is a crystal system characterized by 3 equal and interchangeable axes at equal angle to each other, and usually that is a division of hexagonal system. And this is a system which is less common in the nature and one of the primitive steps. It had a solid bow by 6 similar plates. It is a long and using a vertical axis, one of 3 horizontal crystallographic axis. Each plate will meet a true axis parallel to the third. As you can see in our figure right there, each place of a robot is wrong. And you have a standard axis. Standard axis is A equal to B equal to C, and
excuse me, can you speak louder? I think the quality of the sound is not very good.
And alpha is equal to beta equal to gamma, and less than 90 degrees. If it is equal to 90 degrees, it will become a cube. Next. So we have some example of the robot system. As I said, it's less common and on the primitive cells. And we have some example of the robot system in the nature, which is calcite or cylinder. So this is I'm going to talk about the system of the robot system of symmetries of the robot system. First, I want to talk about the rotational symmetry. Rotational symmetry, as everyone present is symbol as Cn, or we can call it axis of symmetry. The axis of symmetry to the n order is a rotation by 2p over n about the axis map the crystal back onto itself. So we have a question. Can you tell how much axis of symmetry can the robot have? By looking into our figures, can someone tell me that how many axes of symmetry the robot have? Yo, can you answer this question for me?
I think that the axis of symmetry Zubidum has it should be 3. I think it's 3.
3.
Yes, 3.
It's pretty close. The rhombohedron had four axes of symmetry. It had three to four axes in the left figure and only one four axis as the right figure. 1, 2, 4 axis. So there are 4 in all axis of symmetry of the rhombohedron. On vertical axis of 3, 4 symmetry and 3 horizontal axis in the figure of 2, 4 symmetry. Next, we're going to talk about the reflection symmetry or mirror plane symmetry, which is a plane of cell such that when a mirror reflects in its plane is performed, the cell remain invariant. So, and we also have a question that how much plane of symmetry the rhombohedron has. Nan, can you answer it for me?
I think there are 3 axes.
Yes, there are 3 planes of symmetry the rhombohedron have, and each will be like in the figures. All the planes are vertical diagonal in the vertical diagonal position, and there are a center of symmetry too. And we want you to see a video about how the symmetry in the rhombohedron, and you can see it's more curved. Nhưng mà chuyển sang thuyết on ấy, ở cái particle ở dưới rồi, bên trái ở góc bên trái ở cạnh cái dấu tua ấy. Góc bên trái ở cạnh cái tua ấy. Kéo xuống bên trái cạnh cái dấu tua, cái dấu vuông được ở dấu tua ấy. Dưới trái rồi phải đấy, cạnh cái dấu tua ấy, phát đấy dừng nó lại rồi chạy nó lại để cho từng một. Để chạy sang chung. Được. Đấy, chạy nó từ để quay lại từ lại. Tôi biết đâu, không cần phải cô hình đâu, tôi biết. So, as you can see, the mirror plane is exactly divide the rhombohedron in half. Next figure. As you see, and this is a true for axis of symmetry, which will rotate the. As you see, it will rotate the rhombohedron in exactly 180 degrees, and it will be the same. So we can send you the link so you can see by yourself which the axis of symmetry and how the axis and the plane of symmetry and how the figure is divide our rotation around the axis and the plane. This is the end of our presentation today. Thank you for listening.
Okay, so thank you, group number 5. It's very good that you saw the symmetry operator, light or rotation axis plane by the clip. So my video clip is easy for other attendant can observe and see it obviously. Okay, very good. Okay, so any question or comment so far? Is there any question? Okay, so good, thank you. Ok, rất là cảm ơn các bạn. Như vậy thì 5 nhóm này đã trình bày xong cái nội dung mà được giao cho chuẩn bị. Thầy đánh giá là các nhóm đều đã rất là cố gắng nỗ lực để làm thế nào đó thể hiện được là mình đã tìm hiểu và đã cố gắng để đạt được cái yêu cầu mà các thầy đặt ra. Thế thì thầy muốn nhắc lại một số điểm ngắn gọn như thế này. Thứ nhất là bây giờ chúng ta đang trả lời câu hỏi thứ hai. Câu hỏi thứ hai là các nguyên tử phân tử nó sắp xếp thế nào, và nó sắp xếp thế nào. Rõ ràng đây là những cái vấn đề liên quan đến hình học không gian, đúng không ạ? Hình học không gian nó sắp thế nào không gian. Thế thì có mấy cái điểm thứ nhất là một nhóm đầu tiên, nhóm số 1 trình bày là trước đây chúng ta đã học về đường, về mặt phẳng rồi. Qua 3 điểm không thẳng hàng chúng ta có thể xác định mặt phẳng, đúng không ạ? Qua 2 điểm chúng ta có đường thẳng. Thế thì chúng ta có thể nói với bạn mình là tôi muốn xét cái đường này bằng cách là chỉ cho 2 cái điểm trên đường đấy là đoạn thẳng AB, đường thẳng đi qua cái 2 điểm AB chẳng hạn. Hay là mặt phẳng được xác định bởi 2 đường thẳng không song song với nhau là mặt phẳng đó, vân vân, thì là xác định mặt phẳng. Thì bây giờ chúng ta sẽ có một cách xác định mặt phẳng mới, đó là bằng các chỉ số Miller, được chưa? Đấy là cái nội dung nhất. Còn các nhóm còn lại từ số 2 đến số 5 ấy, là các bạn đã giúp là bây giờ nếu theo định nghĩa về cái mạng không gian chúng ta chỉ có 7 hệ thôi, có 7 hệ thôi, và để thỏa mãn tính chất đối xứng. Thế giờ 7 hệ đấy nó khác nhau về cái gì? Khác nhau về tính chất đối xứng. Nhắc lại là cái tính tịnh tiến bỏ đi vì tôi bỏ đấy rồi. Bây giờ chúng ta chỉ quan tâm đến cái một làm thế nào để một ô nó không thay đổi khi chúng ta áp dụng phép đối xứng. Thì các bạn phải chỉ ra là nếu như phép quay thì phải chỉ ra cái trục quay, nếu như mà phép phản xạ thì chỉ ra cái mặt phản xạ, và muốn chỉ ra mặt, muốn chỉ ra đường thì chúng ta học rồi, đúng không ạ? Chúng ta có nhiều cách, hoặc là chỉ ra một đường thẳng, hoặc là một điểm nằm trên đường đó, hoặc là vẽ mặt phẳng rồi, mặt phẳng rất rõ ràng là như nhóm số 5 là các bạn dùng cái clip để chỉ ra cái mặt phẳng nó như thế nào, vân vân. Tuy nhiên thì trong mỗi nhóm thì các bạn thấy là có những cái mà chúng ta chưa hoàn thiện, đúng không? Thì đề nghị các bạn là trong từng nhóm là chúng ta qua góp ý của thầy là hoàn thiện lại, sau đó thì gửi lại cho các thầy cái bản slide để up lên trên CSV các bạn nhóm khác có thể tham khảo để tìm hiểu thêm. Đấy, một lần nữa thì rất là cảm ơn các bạn trong nhóm đã chuẩn bị và cũng trình bày. Và trong các nhóm thì có các bạn trình bày rất là tốt, thầy cũng thích nốt vào đây. Những ai trình bày tốt nhất thì thầy sau này sẽ để cộng điểm, còn những ai mà chưa thì thầy sẽ rút kinh nghiệm trong buổi sau chúng ta sẽ trình bày tốt hơn nhá. Ok, vậy thì chúng ta dừng cái buổi học hôm nay ở đây. Hôm nay rất xin lỗi các bạn có một cái khoảng thời gian chúng ta để chống vì có việc bất thường phải xử lý. Buổi sau chúng ta sẽ tiếp tục các cái nội dung liên quan đến chương 1. Hôm nay chưa được thiết chương 1 rồi thì các nội dung tiếp chương 1 sẽ được giảng trong buổi sau. Ok, rất là cảm ơn tất cả các bạn đã dừng học ở đây hôm nay nhé. Bye bye các bạn.
Em chào thầy.